Hi, I'm Mingyu Derek Ma. I'm thrilled to introduce our work EventPlus, a temporal event understanding pipeline done by our team at UCLA and USC. We'll have a system demonstration at the end of this video. Event understanding is a core problem for natural language understanding. It's intuitive for human. For example, given the show text, a person can infer lots of information, including event trigger and type, event-related arguments like agent, patient, locations, event duration, and temporal relations between events based on the linguistic and common sense knowledge. This understanding helps people comprehend the situation and prepare for future events. This information is also helpful for downstream applications, including question answering, story generation, and forecasting. Researchers have been building NLP analysis tools for core NLP tasks, mostly in token and sentence level. However, systems that target at semantic understanding of events and their temporal information are still unexplored. There are individual works for event extraction, temporal relation detection, and event duration detection, but they are separately developed and thus cannot provide comprehensive and coherent temporal event knowledge. So we present EventPlus, the first event pipeline system providing comprehensive event understanding capabilities, and each component has comparable performance to the state of the art. This figure shows all the components and the system design of EventPlus. Note that our system handles two types of event representations. One represents an event as a trigger word, which has broader coverage. The other represents event as a complex structure, which can provide richer information. Our model combines the benefits of both worlds. Let's look at the first component, the multitask learning of event trigger and temporal relation extraction model. The event trigger extraction component takes the input of raw text and outputs single token event triggers. The input to the temporal relation extraction model is raw text and a list of detected event triggers. The model will predict temporal relationships between each pair of events. This is a multitask learning framework to learn both tasks, and the model fits a BERT embeddings of the input text to a shared by LSTM layer to encode task-specific contextual information. The performance of event trigger extraction on TB-dense and matrix achieves the best F1 scores. We also evaluate the temporal relation extraction module given golden events as relation candidates, and it achieves the state-of-the-art performance. The second component is an event extraction model on ACE ontology. Although event triggers present the occurrence of events, they are not sufficient to demonstrate the semantically rich information of events. Output of this component is event trigger word like toward, event type like movement transport, argument like George Pataki and 5 counties, and argument roles like artifact and destination. It can also detect entities, which are candidates for arguments. This module is built upon a multitask learning framework of trigger detection, argument role detection, and entity detection, and uses the same shared BERT encoder. The model has the following steps shown in the right figure. First is trigger detection. Given a sentence, label the entire sequence with corresponding trigger labels. Second is trigger breakdown. Since each detected trigger represents an event, we'll break down the labeled trigger sequence into individual events. For example, in this diagram, we have 2 predicted events. And third step is argument detection. For each predicted trigger, find its corresponding argument sequence. This is done via attention mechanism. That is, the encoded sentence representation pay attention to each trigger representation and obtain the corresponding argument sequence for each trigger. Hence, there will be 2 argument sequences for this example. We develop the following constraints during decoding based on the predicted entities and other specific definitions in ACE. The first constraint is entity argument constraint, meaning argument must be a predicted entity. The second is entity triggered constraint, meaning trigger must not be a predicted entity. And the third constraint is valid trigger argument constraint. Based on the definitions in ACE 2005, each event type takes certain types of argument roles. So given the predicted trigger label, the argument roles in the sequence can only take those that are valid for this particular trigger. We set the probability of all invalid configurations to be 0 during decoding. We evaluate this module on the test set of ACE 2005 dataset and compare with the state-of-art model 1IE. Our system outperforms 1IE in terms of entity detection performance, but our trigger and argument detection performance is worse than 1IE. Our third component is event duration detection, which classifies event triggers into duration categories. We developed two models for this task. The first is fine-tuned BERT model. The second one is adapted from a model called UDST, which uses Elmo embedding followed by attention layers to get representations of the event predicates. Then the representation is fed into MLP for classification. We use three datasets for training and testing. The first one is UDST dataset with duration categories annotation across 11 types from instance to centuries. The second dataset is typical duration dataset, annotates duration categories for news articles in Temporal, covering 7 duration categories from seconds to years. And third dataset is ACE duration, which annotated by us on samples from ACE dataset, also covering 7 categories. The experiment's results are shown in this table. We evaluate two models trained using different training set combinations on the typical duration and ACE duration dataset. We report accuracy and correlation. So U here represents training using UDST dataset, T means training using typical duration dataset, and T plus U means training using the combined dataset. The results show that the BERT model is better than UDST Elmo-based model in general, and the data augmentation is particularly helpful to improve performance on ACE duration dataset. Due to the limited size of ACE duration datasets, we weight more on the typical duration dataset and select the BERT model trained on typical duration as the best configuration. To the best of our knowledge, this is the state-of-art performance on the event duration detection task. After extracting all possible events using these two event extraction models, we introduce an additional model to identify events that are indicated by speculation or negation keywords. Since those events do not happen, we mark them with special labels. For example, in these two sentences, a not and might indicate the event send troop would not happen. So there are two steps. We first identify negation and speculation cues, and then we detect the sentence partitions affected by these cues. So we use BERT-based cue detection model and a BERT-based scope resolution model and train on the SFU review dataset. And the experiment's results show that the trained model can achieve 0.92 F1 score for cue detection and 0.88 F1 score for token level scope resolution. So we design a pipeline system to enable the interactions among the components, and we'll visualize the collected output from all the components in the user interface. So far, we show a pipeline that targeted news domain. Well, with our flexible design, each component of EventPlus can be easily extended to other domains. Here we show two approaches to extend the event extraction capability to the biomedicine domain. The first one is multi-domain training with JNIA, a dataset containing biomolecular interaction events from literature using shared token embeddings with news domain data. So the model can predict an event in both news and biomedicine text. And the second approach is replacing the current component with an in-domain event extraction component, the CyBERT-FT. So experiment result on the right shows that the multi-domain training improve the performance on JNIA, but still lower than CyBERT-FT. So we use CyBERT-FT to extend the event extraction capability for EventPlus to biomedical domain. Next, my co-author Jiao will demonstrate our live demo.
This video aims to introduce the functionality of EventPlus and how users interact with the system. If this is your first time to use EventPlus, we designed a walkthrough tutorial to get users familiar with the functionality of each panel. If you're already familiar with EventPlus, feel free to click on Skip button to skip the walkthrough tutorial. Users can click on Feature and Task Help button to know what we extract in EventPlus and the meaning of annotations that we are using.
EventPlus is designed to support multiple domains.
For example, let's use EventPlus on the news domain. Users can either select an example input from the drop-down box or freely input any text that they are interested in. Let's go to System website and randomly select a paragraph and put it on EventPlus. After clicking the Analyze Text button, EventPlus will call backend API and get the annotations from the backend algorithm. We show entities and their year labels in panel C1. These detected entities will be candidate arguments for detected events, which we listed in panel D. Users can click on any detected event in this panel and get corresponding arguments of the selected event in panel C1. We also show the role of both arguments and event triggers.
For example, stone is the argument for the convicted event and has the role of defendant.
In addition, we show the temporal relation among events in panel E, where edge labels represent the relation type and the node labels indicate the duration of each event.
The flexible design of EventPlus makes it easy for researchers to adapt it to other domains. For example, we can also support biomedical domain.
EventPlus will also visualize the other events in the same style.